So in this talk, we will talk about the representations of the data. So let me start just by defining what we mean by a representation of the data. A representation for us is any function or stochastic function of the data which is useful for the task we're trying to solve. So how do we define useful for a task? We define it in the sense of how informative it is for the task we're trying to solve. Of course, nothing is more informative than the data themselves for the data processing inequality, but we would like the representation to be at least as informative as the data. And this means that the representation is sufficient. But now, rather than working directly with the high-dimensional raw sensory data, we also want a representation which is, in some sense, more abstract. So between all the sufficient representation of the data, we want one which is also minimal, in a sense that we will define shortly. And another problem with real data is that they are affected by a large number of nuisances that are not relevant for the task. For example, if I'm trying to classify an image, then I don't really care about the value of the pixels in the background or about occlusions or about any fine transformations affecting the image. So for a representation to be useful, I would like this representation to be independent or unaffected by all these nuisances. And then last problem is that when working with real data, the information is not always contained only in the components of the data, but also in the correlations between the components of the data. Now, since it's difficult to extract information from the correlation, for the representation to be simple to use, we would like all the components of the representation to be independent, meaning that the representation is disentangled. So in short, another representation of the data for us is a minimal sufficient invariant representation that is also disentangled. Now, the nice thing about these properties is that it's very easy to formalize them in an information theoretic setting. So precisely, we said that a random variable z is an optimal representation of the data x for the task y if, first of all, it is sufficient, meaning that all the information contained in x about y is also contained in the representation z, where I there is the mutual information. Then we would like for the representation to throw away as much useless information as possible, which gives us the minimality of the representation. Then we would like the representation to be independent from any random variable affecting the data, which is independent from the task y. And if invariance is too much to ask, we would like at least the representation to be maximally insensitive to the nuisances, meaning that it is as little related as possible to all the nuisances affecting the data. And finally, we would like the components to be independent, as measured, for example, by the total correlation of the components, also called the vector mutual information. So now, the name of the game is how do we learn a representation of the data satisfying all these properties. And as difficult as this may seem, it actually amounts to adding the right amount of noise during the training process. But before we get to that, is there any question or any problem with these requirements for a representation? OK, great. So let's concentrate at the beginning only on sufficiency and minimality of the representation. We can rewrite it as a simple constraint optimization problem. And if we write down the corresponding Lagrangian, which is called the information bottleneck Lagrangian after the work of Tishby, we get this loss function. Now, look, for example, at the first term of this loss function. This is exactly the cross-entropy loss, which is commonly used in deep learning, plus an information theoretic regularizer that limits the complexity of the representation we are learning. So this is quite astonishing. We just started from general desiderata of the representation and from information theoretic principles, and still we end up with exactly the loss function that we use in practice, but for a regularizer which we don't use. And in fact, the main point of the talk is that this regularizer is actually used in practice, even if we don't exactly know it. Before going to that, we still have some desiderata that we didn't clear. Even if we minimize the information bottleneck Lagrangian and we learn a minimal sufficient representation, we still want the representation to be invariant. But it happens that a sufficient representation is actually invariant to all the nuisances if and only if it is a minimal representation. To be precise, we can prove that given any nuisance n, the degree of dependence between the representation z and the nuisance is upper bounded only by the minimality of the representation. Moreover, there always exists a particular nuisance affecting the data for which equality holds. This means that the only way I can learn a representation of the data which is invariant to all the nuisances is that I learn a minimal representation of the data. And now, this actually has already a few important consequences about learning invariant representations. First of all, this means that we can use a regularized loss function, such as the information Bottleneck Lagrangian, to learn a representation which is minimal and therefore invariant. So this is actually the most natural possible loss function to use if we want to learn an invariant representation. We can also not use an explicitly regularized loss function. We can instead create a bottleneck in the architecture of the network that automatically reduces the quantity of information in the representation, therefore making the representation more minimal. For example, if we reduce the dimensionality of the representation, for example, using max pooling, or we add noise between channels of the network so that we restrict the size of the communication channel between two layers, then we improve the minimality of the representation, and therefore we also improve the invariance of the representation to all the nuisances. An even more interesting application of this is that if we stack multiple layers, by the data processing inequality, we will always get a representation of the data which is more invariant than all the representation that we will get with less layers. This is actually pretty interesting because it means basically that the more we increase the complexity of the network by adding new layers, the simpler the representation learned by the network actually is. And we will go back to this problem. And the preview is that this is basically solved because the number of weights in the network does not measure, in this sense, the complexity of the network. It's actually the quantity of information contained in the weights that measure the complexity. But we will come back to this. So just to summarize so far, we have decided a few properties, a few desiderata of a representation, and we showed that this reduces to an optimization problem, which is exactly an information Bottleneck Lagrangian. And this information Bottleneck Lagrangian is the common cross-entropy loss function, to which we are adding a new regularizer, which is not commonly used in practice. And we also proved that these few definitions already have strong implications, and precisely that the minimality of the representation is equivalent to the invariance. And this allows us to prove that stacking more layers always improves the invariance of the representation. But now we have a problem. Modern architectures do not use any of this framework. They don't use any kind of, or at least, even if they use regularization, they work without any explicit regularization. So for the most part, right now, the training process of, so the training of a deep neural network is a black box process, which is completely oblivious to the representation learned inside the network. So the key question now is, why do we always learn a good representation of the data, even using a training process which doesn't care at all about the representation that we are learning? And the point that we will prove is that this is related to the particular architecture of a deep neural network, to the particular algorithm that we are using to optimize the deep neural network, and to an important kind of duality that we have between the weights of the network and the activations of the network. And this naturally leads us to the second part of this talk. So until now, we have talked about the layers of the network as a representation of the input of the network. Now we can also think about the weights of the network as a representation of the training dataset. In fact, the weights are a stochastic function of the training dataset, and hopefully they are sufficient for the network to solve a task. So since we have now two kind of representations, what we care about is how they are related to each other. And So to set the stage for this, let me start by writing down the common cross-entropy loss that we use and decompose it in an information theoretic way. So first of all, the cross-entropy decomposes as the intrinsic error. This is the error we will commit in classifying the dataset, even if we knew the right parameter of the distribution generating the data, and so there is nothing we can do about this. Then we want the weights to be sufficient, meaning that all the information that the dataset contains about the parameters theta should also be contained into the weights. And we want the network to be efficient, meaning that it should use the information contained in the weights in the best possible way. But now there is a last residual term, which is the only negative term in this expression, which is how much information the weights are memorizing about the dataset, even if it is not informative at all about the underlying data distribution generating the data. So the problem now is that a network can choose to minimize the cross-entropy by just maximizing this. That means by just memorizing the dataset, and this is just pure overfitting. Now, we can prevent this game by adding back this term to the cross-entropy loss, so annihilating its effect. Unfortunately, computing this term is intractable. But what we can do now is to add an upper bound to this term, which is the information contained in the weights. And what we end up with is a loss function which pretty much looks like an information Bottleneck Lagrangian. But this time, instead of trying to infer the optimal representation of the input, we are trying to infer the weights, which are a representation of the training data. And it is minimal if and only if we are not memorizing anything about the dataset, which is not relevant for the task. So now we have two different information Bottleneck Lagrangians into play, the one for the layers and the one for the weights. And we want to know how these two are correlated. And this is the quick question that explains why invariance and disentangle emerge in learning a representation in the deep neural network. But before going there, let's see if the theory we developed so far already has some kind of predictive power. So in the recent paper by Sammy, it was shown that if a neural network is always complex enough to overfit to random labels. So if we look at this illustration by Ben Recht, we see that this basically means that deep models are always on the far end of the complexity axis. Nonetheless, they seem not to suffer from the bias-variance trade-off. On the other hand, in our theory, the complexity of the network is not measured by the number of parameters. It's actually measured by the quantity of information that's contained into the weight. Moreover, we predict that for random labels, we should transition from an overfitting regime to an underfitting regime precisely at the critical value of the regularizer beta equal to 1. And this is exactly what we can see here in the plot to the left. So each point of this plot is a neural network trained on CFAR for a different dataset size and for a different value of the regularizer. Above the critical value of the regularizer beta equal to 1, the neural network always overfits to random labels. When the regularizer is stronger than 1, the neural network never overfits to random labels. And the critical phase transition happens exactly at beta equal to 1, which is the dashed line here. And I would also like to notice that this works even if the dataset size is just 100 samples. So this particular regularizer can prevent overfitting for a real convolutional neural network, even with only 100 samples, and we can predict the transition between overfitting and underfitting. For real levels, on the other hand, the situation is very different. We predict that even when the regularizer is stronger than 1, we should still be able to fit the data, but this time without memorizing anything. And this is exactly what happened. In this regime, we fit and overfit to the real data. In this regime, we fit and don't overfit too much on the real data. OK, so even when the network actually overfits to the random labels, it has to pay a price to do this. In particular, it needs to increase the quantity of information it needs to memorize into the weights. Precisely, we can see in these experiments that increasing the number of random labels in the dataset, the quantity of information needed to overfit increases, and the amount of increase is of the same order of magnitude of the size of the labels that it needs to memorize. And finally, we can reparameterize the testing error as a function of the quantity of information into the weights. And we see that we recover exactly the trend predicted by the bias-variance trade-off. So this measure of complexity is much more compatible with the bias-variance trade-off than the number of parameters of the network. OK, so we still have a problem. Everything we have done until now is if we regularize the network to have a constrained amount of information into the weights.
What is the regularizer?
The regularizer we're using is the quantity of information in the weights. So now, of course, the problem. Yes. Exactly. So this is made possible by this work by Kimma, variational dropout. Basically, what we do is to model the posterior of the weights given the dataset as, let's say, a Gaussian distribution, actually a log normal distribution. And then we can use stochastic gradient variational bias to optimize, instead of optimizing the point estimate of the weights, we estimate the best parameters for the posterior distribution of the data. And once we have the posterior and we fix a prior, we are able to compute the mutual information. So all the details are both in our paper and in Kimma paper. So is there any other question regarding these experiments? OK. So now the problem is that this is if we use a regularizer, but as Tommy pointed out in his talk, real neural network seems to perform pretty well without any explicit kind of regularization. And this seems to be related to the flatness, so to the fact that stochastic gradient descent converges to minima that are flat. But in fact, flat minima are exactly the minima that have low amount of information. More precisely, we can prove this bound, saying that the quantity of information contained in the weights is upper bounded by the nuclear norm of the Hessian, which is minimized exactly when the minima is flat. And I should point out that this does not contradict Semi's paper on the sharp minima, because the bound is only in one direction. A sharp minima can either have a low or high amount of information. So stochastic gradient descent converges to flat minima, so to low information. So it implicitly regularizes the quantity of information. And so we don't care about adding the regularizer. Stochastic gradient descent is already adding exactly this regularizer for us. And so we can think that all this theory still applies to a common neural network. Now, the very last thing that we need to do is to connect these two things, the representation that we learn in the layers and the representation of the weights that we learn. So the minimality of this, which is connected to invariance, and the minimality of this, which is connected to non-memorization of the dataset. And the relationship is actually pretty clean, at least in the case of one single layer. For a network with one layer, the quantity of information in the activations plus the total correlation of the layer is strictly bounded by an increasing function of the quantity of information in the weights. Said in another way, it means that the less information is in the weights, the less information is also in the representation of the input data, and the less entangled the representation of the input data is. Therefore, if we train the network either using an explicit regularization that reduces the quantity of information in the weights, or we train with stochastic gradient descent that also reduces the quantity of information in the weights, in both cases we learn a representation of the data which is both more minimal and therefore more invariant to all the nuisances by the preceding theorem, and more disentangled because we also minimize the total correlation. So this is a general property and derives from the fact that you can think of a weight with low information as a weight in which you can add the noise without changing anything. So noise in the weights is actually perfectly equivalent to adding noise to the activation. So if you have noisy weights, so weights with low information, you also have activation with low information. So gradient descent will not give you a good quantity of information in the weights, so this bound is completely useless in that case. Oh, and this is for one layer, but we can also generalize this for multiple layers. It's a slightly more complicated expression, but we can still do that. And we can check this in experiments. So now you can see that if we decrease the quantity of information in the weights, the invariance of the representation to this occlusion nuisance that we added to MNIS start increasing. So it's more and more invariant, and the less information is into the weights. And the behavior of the independence, of the invariance, follows the prediction from the theoretical bound. OK, so to summarize, we have presented the use of the quantity of information in the weights as a measure of the complexity of the network. I should say this was already proposed in 93 by Hinton, actually. And so now we can actually compute everything, and we can optimize for this, though. And we have seen that this prevents overfitting, exactly as predicted by the theory for random labels, and it connects to flat minima. We also studied the representation of the data, and we have seen that they are maximally insensitive to nuisances if and only if they're minimal. And this gives us a tool of studying invariance properties and proving properties, and give a way of learning such representations. And finally, we have shown that the quantity of information in the weights bounds the quantity of information in the representation. And this says that a network trained with explicit or implicit regularization is always biased toward learning representation of the data, which are both invariant and disentangled. So if you have any question, I will be happy to take them.
Okay, so I have one question. It's about the... I'm here.
What?
Here.
I'm sorry.
Yeah, I was wondering whether with a measure of complexity you can study existing regularizers, for example, sparsity or to regularization.
Yes, so we actually can. So for L2 regularization, you can also see that the L2 norm of the weights appears in this bound. So if you minimize the L2 norm of the weights, you are also minimizing the quantity of information in the weights. So they're related in this way. And about sparsity, there is a paper called Variational Dropout Sparsifies Deep Neural Networks, and in which they basically prove that so if a network if a particular weight has basically no information, it means that I can delete that weight and the network wouldn't care at all about this. So it gives an explicit way of sparsifying the network, and this also works in experiment. So,
I'm going to talk about this paper.
OK. Great.
OK. And I have one more question concerning this phase transition. Is it mathematically proved or just empirically shown?
No, this is this is an experiment with a real neural network. We're using exactly the same experimental setting as the understanding generalization paper, and there is also a theoretical proof, which you can see from here. So there is a trade-off between. So if I memorize a label, I minimize the cross entropy by I increase the mutual information. So when beta is equal to 1, I don't care if I minimize the cross entropy or increase the mutual information. For beta less than 1, I prefer to minimize the entropy. For beta more than 1, I prefer to do this. So it's exactly this trade-off.
OK, right. Thanks.
So let's see, in terms of the implicit regularization of stochastic gradient descent, I think you gave two explanations, if I'm not wrong. One is the noise in the weight, the activation, but implicit.
Yes.
And the other one is flatness of the minima. Exactly. Is that the same explanation? Or?
Yes, actually, yes. So the point is that if you have a minima which is very flat, even if you add noise to the minima, you will end up in the same point in the valley, so the loss function will not change, and so you still have a good trade-off here. So if the minima is flat, you can decrease a lot of information, increase a lot of quantity of noise, and still the cross entropy won't change. And so this is exactly the relationship.
Okay. Yeah, so this fits what we have done, but it's a different perspective. There is no, in classical learning theory, a big part is empirical processes, right? It's not directly probabilities. That's not what you have. You have just samples, right? So, for instance, convergence of the empirical error to the expected error. I don't see where this comes in. This is a kind of unusual approach from the point of view of, when I say classical learning theory, I mean Rademacher averages, VC dimension, and so on and so forth.
Yes. Okay, I'm not sure I understand completely the question. Maybe we can talk more offline. But what I can say right now is that this is actually a generalization of variational learning. In the case beta equal to 1, this Lagrangian is exactly the variational lower bound to the marginal distribution of the data. So the critical value beta equal to 1 for which the phase transition happens to be the variational inference loss function. And so this is kind of a generalization of bias learning, if we want. Yeah, so maybe we can talk about it later.
Time for one more question. Okay, let's thank the speaker again.
Thank you very much.